Many of the idealized gas power cycles that we'll study involve reciprocating engines, so engines that include pistons and cylinder devices. These pistons allow for easy compression and expansion of gases so that we can extract a net amount of work from the engine. To understand these engines, we have to have some terminology that goes along with those engines themselves. So if you look on the left side of the slide, you'll see a piston at the bottom of the cylinder. Now normally we draw it on the board upside down from what it is here, but this is the way it's usually set up in a real engine, with the valves at the top that can open and close to allow air and fuel in and out, and then the piston moving up and down from the bottom of the cylinder. Anyway, on the left-hand side in Figure A, you'll see the displacement volume shown there, and the displacement volume, though, is different than the volume of the system, the air above the piston at bottom dead center. See, the piston only moves so far. It moves down so far, it moves up so far, and then goes back and forth between those two positions. So the volume of the chamber above the piston, when the piston is at the farthest length of its stroke down, is called the volume at bottom dead center. It's the maximum volume that the cylinder experiences. Then as the piston moves up, it finally reaches another point where it stops and begins to travel the other way, but that point where it stopped is called the volume at top dead center, or the volume that remains when the piston's at top is the volume at top dead center. Now that's the minimum volume, and there's always some volume. You can't squeeze the air and the fuel mixture down to nothing. You blow the head off the engine. That doesn't work. So anyway, that's the maximum and minimum volume. And the difference between those two is what's called the displacement volume. And so you'll see in Figure A that the displacement volume is the volume of the system that's displaced by the piston. Now the compression ratio is just the ratio of the maximum volume to the minimum volume. In other words, the volume at bottom dead center over the volume at top dead center. Now be careful about this, because the volume at bottom dead center is not the displacement volume. Those are two different things. The volume at bottom dead center equals the displacement volume plus the clearance volume, or the volume at top dead center. So the compression ratio is simply defined as that ratio of volumes. Understand the compression ratio is always going to be greater than 1. Now, there's another interesting parameter of these engines that you may have heard of before. It's called the mean effective pressure. You may have heard it and not known what it meant. You may have thought that maybe it's some type of average pressure for the actual engine. Actually, it's sort of a volumetric efficiency. Think about it this way. If you look at whatever cycle the engine operates on a PV diagram, the area enclosed by that cycle represents the amount of work that the engine produces, or the net amount of work that the engine produces during one thermodynamic cycle. Now I keep saying thermodynamic cycle. Understand that in a typical 4-stroke engine that it takes 2 revolutions of the crankshaft to equal 1 thermodynamic cycle. So that's why I keep referring back to it. But anyway, back to mean effective pressure. If you wonder, say, whether the let's have some fun with this. Let's say you wonder, is the Ford engine or the Chevy engine better that displaces 300 cubic inches, let's say. Now, if we were in class, I'd normally have people raise their hands and say who's a Ford fan or a Chevy fan or an import fan. I guess you can raise your hand virtually, but the question is, given 2 engines with the same displacement, which engine is the better engine? Another way of asking that is, which engine produces the most power per cubic inch? Right? That's one way. Not necessarily which engine is the most efficient in terms of fuel economy, but which one produces the most power per cubic inch. That's the question that mean effective pressure answers. If you think about the area inside of that cycle, that area represents, as I said, the net amount of work the engine produces in 1 thermodynamic cycle, or 2 rotations of the crankshaft. Well, that area could be represented in another way. If we imagine taking the piston cylinder device, laying it on its side so that you can see the maximum and minimum volume positions of the piston, we could define the mean effective pressure to be the pressure required so that for the same max and minimum volume, the area beneath that mean effective pressure line is the same area as what's in the cycle. And so that's written in equation form down below the figure on the right-hand side. It says that the net work equals the mean effective pressure times the displacement volume, which is piston area times stroke. And so if you have a 300 cubic engine or 300 cubic inch engine that produces horsepower per cubic inch, and one that produces 2 horsepower per cubic inch, then the second engine that produces 2 horsepower per cubic inch, it has twice the volumetric efficiency of the first, because what it's doing for each cubic inch is producing more horsepower, producing twice, as a matter of fact. Now this is less of a comparison, how can I say this? It has less to do with the work and more, this equation has to do with the definition of mean effective pressure. So if you look at the next equation in the box, which is what you really need to understand, it's just the amount of work produced per displacement volume. That's what it really is. That's what mean effective pressure really is. And you can write that as a total amount. In other words, the total net work produced divided by the total volume displacement, or the work produced per unit mass divided by the volume displaced per unit mass. Either way works just fine, but this is just a measure of the performance of an engine in terms of its volumetric efficiency and how well it uses the volume it displaces to produce horsepower. So finally we get to our first cycle. This is the cycle that would be much like the spark ignition engine in the car you probably drive. I drive a diesel. It's a little different than this. But let's go through the ideal Otto cycle first of all. And what we'll do is we'll develop it to compare the real cycle with the ideal version of that cycle. Now, let me warn you, by the time we're done with this, we actually won't have a model that is fine enough to differentiate between a piston cylinder driven engine and a rotary engine. You notice the animated graphic over to the right. It's showing the volume or the system that is on one side of a rotor of a rotary engine. If you've never seen a rotary engine, you should pause the video and go look one up. They're pretty neat. Basically, they have a lobe, almost triangular shaped actuator instead of a piston, and all 3 sides of that actuator are involved in some part of the thermodynamic cycle at one time. So it's kind of like having one rotor in a rotary engine is kind of like having 3 pistons. And that's why rotary engines like this can produce so much horsepower for such a small size, because it's fairly efficient in terms of the number of sides that are active at one time and the effective number of pistons that you've got there. But you'll notice, and I'll try to talk through this, hopefully the audio syncs up okay, but as the system comes around, here's the exhaust, and right there where you've got that small blue shape forming, that's the intake. You notice the volume getting bigger. Fuel is of course added, and then here the spark plugs ignite that air-fuel mixture after it's been compressed, and then you see it's red, it's hot, it's expanding, driving the rotor around and then exhausting out the port there. Like I said, this Otto cycle will represent a rotary engine just as well as a piston cylinder engine, although any of you that have dealt with those engines know that there are significant differences between those 2 engines. But again, this is a crude enough model or a coarse enough model that it doesn't differentiate between the 2. So let's continue and let's go from the real piston cylinder device to an idealized version of it. We're going to start on the compression portion of the real PV diagram up at the top. And so what happens in the real piston cylinder device, the real engine, is that the valves at the top are closed and the piston moves up, compressing the air-fuel mixture. Now understand that by this point the fuel is pretty much atomized. It's a gas as well. And the compression stroke is moving us from bottom dead center to top dead center, so moving to the left along the volume axis just before the point labeled ignition. Now in our idealized version of this process, look at the lower row. There's the move from state 1 to state 2, which is again a compression process where the piston is moving up, just compressing air, no air-fuel mixture here. But we're assuming that there's no heat transfer during this process. And so no heat transfer, the air is getting hotter, right, because we're putting work into it, its temperature is going up, we're increasing the energy in the air. But we're moving from state 1 at bottom dead center to state 2 at top dead center along an isentropic path. In other words, we're going to make this reversible. This is going to be a reversible process. No heat transfer And reversible means that it's isentropic. So this is an isentropic process. Why do we make this isentropic? I mean, it doesn't seem fair, right? To say that the piston moving up is a reversible process doesn't seem fair, because you know that in the real process, or in the real engine, there's going to be friction, right? And friction is an irreversibility. There's going to be fast compression of the gas. And so there's going to be a pressure variation throughout the entire system. And so it seems unfair to say that we're going to call this reversible. Well, again, remember, we're pretending the potato is a sphere of water. We're idealizing things so that we can actually analyze it. The other piece to making this isentropic is that there can't be any heat transfer. And you might say, well, in a real engine, if you don't have heat transfer, the engine's going to melt down. That's true, but think about the amount of heat that's lost from one charge of air as it's compressed. The compression process happens so fast that the amount of heat loss from that little quantity, or that single charge, is fairly low. So this is not a horrible approximation. It's supposed to get us in the ballpark. So the idea that the first process is an isentropic compression is not such a bad approximation. In the real engine, the next thing that happens is ignition of the gases. So going from the point in the upper row labeled ignition to end of combustion, that happens pretty quickly. It's not instantaneous, of course. If it were, it destroys your engine. That's called engine knock or detonation. You don't want that. There is, of course, a flame front that spreads out. But by and large, the piston doesn't move a whole lot, because remember, it's at top dead center, and so it doesn't move very fast near top dead center anyway. If you know anything about the kinematics of an engine, you know that the piston is moving at its highest velocity near the center of the stroke. And so it's actually moving fairly slowly at top dead center and bottom dead center. And so the approximation that the piston essentially remains still that we're going to use for our idealized system, our idealized cycle on the second row, is not a bad approximation. So you'll notice the move from state 2 to state 3, where heat is added on the bottom row, and that approximates the combustion process that occurs in the real engine. Now, understand that during that process, we're going to assume that the piston simply stays still. So you'll notice in the idealized diagram that from state 2 to state 3, that's all at one single volume. In the real engine, the next thing that happens is there's expansion, right? The piston moves down where the gases push the piston down doing work. This is our power stroke, where we get the power to drive the car down the road and also to compress gases in other pistons, but for right now, let's not worry about that. And of course, in the real engine, what's going to happen is the exhaust valves are going to open, the piston's going to move up, pushing the exhaust gases out. Now, we're going to kind of condense that a little bit, and in particular, we're going to neglect the exhaust and intake strokes themselves. If you look at the real cycle diagram on the first row, what you'll notice is the bulk of the area enclosed is by the section for compression, ignition, end of combustion, expansion. That upper area there represents the net amount of work just about that we get out of the cycle. Because if you look at the area enclosed around the exhaust intake portion, in other words, if you consider the amount of work required to push the exhaust gases out through an open exhaust port and to pull fresh charge of air and fuel mixture in through an open intake port, it's really not that much work. It's not enough that we should worry about that section. So basically, we're neglecting in our idealized cycle the whole intake and exhaust process and the amount of work required to push the piston up, pushing exhaust gases out, and pull the piston down, pulling, or more accurately, the atmosphere pushes air in, but pulling air in, if you will. We're neglecting that whole piece. So just that upper enclosed area is what we're taking into account for our idealized cycle. And the justification for that is that it represents the larger amount of work by far. So going to our processes in the idealized cycle, you'll notice that from state 3 to state 4, we have again another isentropic process, meaning that we're assuming there's no friction, we're assuming there's no heat transfer, there's no other irreversibilities, and basically the piston simply moves down with the hot air pushing it down, and that's where we get our power stroke from, or how we're modeling our power stroke. In the real engine, of course, the next thing that happens is that the piston moves down, pulling in a fresh charge of air, and then it's back where it started. However, in the idealized cycle, what we're going to do is just let the piston sit at bottom dead center and have heat transferred out. So that's the process from state 4 to state 1 in the second row, where heat is being transferred out of the system. Now, this is not such a bad approximation. Again, understand the piston is not moving, and so there's no boundary work associated with this. Whereas with the real cycle, essentially what happens is you start with exhaust gases, right? You push the piston up, that pushes them out, and then you come back down with fresh air. Well, we're just letting the piston sit still because we can neglect all of the work required to do that little bit of the real process. And instead, we're just letting the piston sit at bottom dead center and do essentially the same thing, which is transfer heat out of the gases so that it's back where it started at state 1. So the first row represents the real engine, and the second row represents our idealization of a spark ignition engine. Now, we have to wrap a little bit of math around this, so I've included the ideal cycle diagram from the previous slide, and I've also included a TS diagram of the same process. Now, at this point, I'm sorry I don't have my textbook in front of me. I should have thought of this, but I didn't. You need to find the ideal AutoCycle in your textbook, and you need to put a tab on that page with AutoCycle on it so you know where to find it. So look for both this PV diagram and this TS diagram, and I think if I remember right, they're on 2 different pages. But make sure you've got those marked, because when you're performing cycle analysis with all these idealized cycles, you really need to have the cycle diagrams in front of you until you kind of commit them to memory. Another thing to note about this, you have to be really careful. Notice in the PV diagram that state 1 is on the lower right, but on the TS diagram, state 1 is on the lower left. So I guess because of human factors, most people want to think that the state in lower right of the PV diagram is the state in lower right of the TS diagram, but that's not the case. Those are 2 different state numbers. So lower left on the TS diagram is state 1, lower right on the PV diagram corresponds to that same state. Okay, so if you're trying to follow it around and make sense of these 2 together, you'll notice that from state 1 to state 2 on the TS diagram is isentropic, and you can just see it because the entropy remains constant. It's a vertical line. On the PV diagram, it's labeled as isentropic, but there's a large volume move from state 1 to state 2 with increasing pressure. So the cycle consists of state 1 to state 2 isentropic compression, state 2 to state 3, constant volume heat addition, remember that represents the burning of the fuel in the real engine. State 3 to state 4 is isentropic expansion, that's the power stroke essentially, and then 4 to 1 is the constant volume heat rejection, where in the real cycle or the real engine, obviously the piston moves up to push exhaust gases out and down to pull in a fresh charge of a fuel-air mixture. Since we can assume that we're talking about a closed system the entire time, understand that we never pull the air out of it. It's just a piston cylinder device moving up and down, transferring heat out, in and out at various points. Since that's the case, we can analyze it with a closed system energy balance. So here we have our closed system energy balance, Q in, Q out, work in, work out, and the change in internal energy of the air above the piston, all listed there together. So, for example, if we apply an energy balance to the process from state 2 to state 3, remember what that is, that's where heat's being added, that's basically where the fuel's being burned in the real system, then the amount of heat added would be equal to the internal energy change of the air. Now, where'd all the other terms go? Well, there's no heat flowing out, or at least we would neglect any heat that's lost. There's no work interaction because we're assuming that the piston stays stationary at top dead center, remember that? So since there's no movement of the piston, there's no work, and all those terms simply go away. Now, the internal energy change between the 2 states, states 3 and 2, can be represented as the constant volume heat capacity times the change in temperature. Now, it's not the constant volume heat capacity because the system remains at constant volume. It's the constant volume heat capacity because we're interested in the internal energy change of the air, and that's what correlates to CV, not so much the fact that the piston's sitting still. Now, that same process, you have to be careful, that same process is, again, state 2 to state 3. It's the upper curve where it says V equals constant Qn at the top. Now, unfortunately, I clicked a little early, and I also have the energy balance for the process where the real engine pushes out the exhaust gases and pulls in a fresh charge of air-fuel mixture. Now the energy balance for that's over on the right-hand side in the PV diagram. Unfortunately, there's a line kind of covering it right now, but that's the Q out process, the place where the piston essentially sits at bottom dead center and heat is transferred out of the air. Okay, so that's from state 4 to state 1. If you look at the TS diagram, it kind of makes sense, right? Because if the air's sitting there and heat's coming out of it, well, that means the entropy is decreasing. So it's not a surprise the state 4 to state 1 moves to the left on the entropy axis. It's also not a surprise that if the piston's sitting still, so there's no boundary work, and, pardon me, and the piston's sitting still, so there's no boundary work, and there's heat flowing out, well then the temperature of the air is going to drop. And so it's not a surprise that from state 4 to state 1, there's a move downward as well during that process. So here's our energy balance. Again, there's no work interactions. There's only heat flowing out as far as we're concerned. And so CV delta T between those two state numbers allows us to quantify the amount of heat that flows out. All right, what about the other two processes, the compression and expansion processes? Well, we will apply an isentropic equation to each one of those in order to understand them. You could apply an energy balance, it's just that the energy balance doesn't really help us a whole lot. The energy balance here would involve work transfer and no heat transfer, and of course the change in the thermal energy of the air that's doing the work or that work's being done on. But that won't help us very much for what we're developing, so let's just look at the isentropic equations that relate the two states, because after all, if the process from state 1 to state 2 is isentropic, we can apply an isentropic equation, whatever happens to be useful. Remember, we've got the first, second, and third isentropic relationships. I'm going to choose the one that relates temperature to volume. Why? Well, remember that for reciprocating engines, the compression ratio is a parameter we typically know. If that's the case, then we know how the volume changes between the two states, where the piston moves from bottom dead center to top dead center and back. If that's the case, then we could relate the temperature difference in those two states to the volume ratio, which is something we know. It's the compression ratio. So that's what's being written here for the process from state 1 to state 2. Of course, the expansion process, state 3 to state 4, occurs on the PV diagram just as it does on the TS diagram. I just pointed to the other diagram to show you the process. And we're applying another isentropic equation to the expansion process from state 3 to state 4. All right, so if we take all these equations and put them together, just getting rid of the diagrams now, if we're interested in thermal efficiency, well then the thermal efficiency of the Otto cycle is just 1 minus Q out over Q in, just like any process, right? If you put heat in and it doesn't come out as heat, it must have come out as work, and so that's basically where this equation comes from. So we can replace Q in by our energy balance, CV delta T. We can replace Q out by the other energy balance. And if you look at it, well, that just means that the heat capacity, CV, cancel. Okay, that's fine. And it's not real obvious. There's a lot of algebra here, but you can see T1 and T2 in the thermal efficiency equation, and you can see T1 and T2 in the isentropic equation. Similarly, you can see T3 and T4 in the other isentropic equation. So it's not like we just plug these in directly. That would be a mathematical or an algebraic mistake. Instead, we work it in with algebra. Here's the result. I won't show you all the algebra, but here's the result. The thermal efficiency of a spark ignition engine is 1 minus 1 over the compression ratio R to the power of the heat capacity ratio minus 1. This is a really interesting, very unique result. It's very useful to us. Why? Well, because we can learn some lessons from it. If you think about it, as the compression ratio increases, the thermal efficiency of the Otto cycle increases. In fact, you look at the first chart or figure on the left-hand side, and you'll notice that the thermal efficiency of the Otto cycle is increasing as compression ratio along the x-axis is increasing. So the maximum theoretical thermal efficiency depends on the compression ratio in a very direct way, and that's good to know because it tells us that even though this is not a perfect model, okay, even though this is a sphere instead of a potato in the oven, if we can take a Otto cycle or a spark ignition engine and increase the compression ratio, we should be able to get a higher efficiency out of it, and that's something worth knowing. Okay, So the typical ratio for an actual engine is anywhere from about 7 to 1 to 10 to 1. Anything above that and the gasoline likes to start burning on its own because the air temperature goes up too high and you get detonation, which is a problem. Now, the other factor in the efficiency equation is K, the ratio of heat capacities for the working fluid. Now, this is not something we have a lot of control over. You can see theoretically we could vary the efficiency of the engine based on the ratio of heat capacity, Cp over Cv, for whatever working fluid we choose, but really our choice of working fluid is always air because it's what's around us. So pretty much K is set at 1.4. There's not much we can do about that. The thing we do have control over, however, is the compression ratio, and that makes a significant difference in the efficiency of the engine.